Good day, everybody. This is Chris with the Ancient Scholar. Today, what I'd like to do is I'd like to spend a little bit of time talking about a relatively confusing concept in pharmacology. Specifically, it deals with a pharmacokinetic concept, and that is the concept of the volume of distribution or the apparent volume distribution. And I understand that this is confusing for a lot of people, and it's certainly caused some confusion in the pharmacology course that I'm teaching this semester. So I wanted to plant a flag on the volume of distribution and then drill down into how we get to it, what it actually means, and what the real implications are of the apparent volume of distribution. Okay, so what we're going to do is we're going to start and we're going to make some real basic assumptions. And then we'll build up our intuition from there, and hopefully this will make a little more sense. Okay, so the first thing that I want to do is I want to talk about the human, and much of pharmacology, our reference model for pharmacology is going to be a healthy 70 kilogram adult male patient. Right? That tends to be our reference model, our generic patient. And when we look at a 70 kilogram patient, a healthy 70 kilogram patient is going to have total body water, right? The amount of water within their body, all right, is approximately 60% of their body weight. So what I can do is I can go 70 kilograms, I can multiply that by 0.6, and that'll give me about 42, and I'm just going to make that 40 liters just for simplicity. So we can model the human, we can model an average healthy 70 kilogram human being as a glass that's full of water containing 40 liters, right? So this is just a model here. Okay, this is not exactly real life, but it's, it's a rough approximation, and we can use this as a basis for developing some understanding, and then we can add more complexity to this model a little later on. So let's start here. So let's imagine that the human being is a bag or just a glass, and then that glass contains 40 liters, right? So this is our human, all right? And hopefully you can understand where I got the 40 liters, right? Because we know that, right, 60% of the total 70 kilogram weight will be water, and that's 40 liters. Okay, fair enough. All right, so let's now talk about how we test drugs in pharmacology. And one of the most important things that we can do is we can measure the concentration of a drug in the plasma or the serum. Okay? And for most practical intents and purposes, plasma is the same thing as serum. I believe serum is plasma that has had the clotting factors removed, but it's more or less the same thing. And so why do we do this? We know that many drugs don't actually work in the blood plasma, right? A lot of drugs work outside of the vascular compartment within tissues and cells, and they act upon receptors that are not in the blood vessels. And so why would we just not measure the concentration of drug in the areas of the body where it works? Well, the reason is because it's really damn hard. And frankly, it's very easy. It's very easy to draw a sample of blood and measure the concentration in the blood, right? So imagine that I have a little sample of blood here, right? So here I have a little Vacutainer vial, and I've got some blood in there, and I take that and I put that in a centrifuge and I spin it down, and when I do that, all of the packed components, right, that have a lot of mass, right, accumulate at the bottom, and then the plasma, actually, the lighter stuff accumulates on the top, and it is in this plasma or this serum, and that's actually where I assess the concentration of the drug. Okay, fair enough. Now, another thing that we're going to do here to simplify the concept and to maximize high-yield understanding is we are going to give a medication via IV bolus or IV push. And the reason that I'm going to do that is when I give a medication IV, I bypass the absorption. I bypass the absorption phase of pharmacokinetics. So I don't have to worry about disintegration. I don't have to worry about first pass metabolism. And I don't have to worry about taking bioavailability into account. I can just assume that if I give a medication IV push, 100% of that IV will make it into the systemic circulation. Okay, so far so good. So now what I want to do is, before I go any further, I just want to imagine that I take a cube. Let's take a cube of sugar here, and imagine that I were to drop this cube of sugar into this water. What would happen? Well, the sugar, right, would be more concentrated here when it got dropped into the water, and then it would diffuse out throughout the water, right? And eventually, I give it a little bit of time, that sugar would evenly distribute itself throughout that water, right? It would dissolve and evenly distribute itself, and then I could wait a little bit of time, and then I could measure, and I could take a little sample of water here, right? And I could measure the concentration of sugar in the water there, and concentration is just equal to mass divided by volume, right? I could take 1 milliliter of that, and I could measure the volume in 1 milliliter, or 0.5 milliliters, or 10 milliliters, or whatever, right? And assuming that this is evenly distributed, right, it diffuses out evenly, I could take a sample from here, and then I could take a sample from over here, and I should get, right, so this is sample 1, and this is sample 2, I should roughly get a concentration in sample 1 that is roughly equivalent to the concentration in sample 2, right? That's assuming that it diffuses out evenly, right? So that gives us an idea. If I sample the concentration in one area of this 40-liter collection of water, if I measure the concentration in one area, I should have roughly the same concentration in another area. Okay? Cool. Now, we know that's not exactly the case in real life, but let's start here because this is going to form the basis of understanding. Okay, so there we go. Well, I could do roughly the same thing, right? I could take 100, let's just do 100 milligrams of some drug, right? I could load that drug up. I'll draw a little syringe here. I could take 100 milligrams of a drug, and I could introduce 100 milligrams of that drug into the vascular compartment, right? And I could dissolve that 100 milligrams of drug into the human body, right? And so if I did that, right, I injected 100 milligrams of that drug, I would expect that drug to diffuse out, okay, wait a little bit of time, and that drug should diffuse itself throughout and should dissolve more or less evenly throughout the 40 liters of body fluid that we have. And then if I measured the concentration of blood, I could measure the concentration of blood, from a vein in the arm, and then from a vein in the other arm, and the concentration should roughly be the same, right? Okay, that's the motivation for now. Okay, that is to say that the concentration of the drug in the plasma, right, I could extrapolate that and go, well, that should more or less be the concentration of drug throughout the body, right? Okay, so now what we do is once we give a drug, so we give 100 milligrams of a drug IV push, we'll say, right? And then what will happen is I will measure the concentration of that drug after I give it IV push. And this is in fact how we calculate the volume of distribution, or more properly or more correctly, the apparent volume of distribution, or the AVD, because it's not a true literal volume. This is not to be taken literally. This is more of a metaphor for understanding what's going on. Okay. And the formula for the apparent volume of distribution is going to be the dose of the medication divided by the plasma concentration, or more appropriately, more generally, the actual amount of that drug that made it to the systemic circulation. But for our purposes, we're giving it IV, so it's the whole dose. It's a whole 100 milligrams. So let's just kind of work through a problem here, if you will. So let's say that I give 100 milligrams of a drug IV push, right? And then I wait a little bit, allow it to diffuse throughout the body, and then I measure the plasma concentration of that drug. So I draw a little sample of blood, spin it down, take a little sample of plasma and or serum, and I measure the concentration of the drug. And let's say that I get a concentration of 2.5 milligrams per liter. So there are 2.5 milligrams of drug dissolved in every liter of body water, this patient, okay? So let's go ahead and calculate the volume of distribution, right? So the AVD in this case would be the dose, which was 100 milligrams, and then the plasma concentration, 2.5 milligrams per liter, right? Okay. So the first thing that you need to understand is when we divide, there is going to be something that is going to divide out of this. Let me just change colors here real quick. So the milligrams are actually going to cancel out, right? And so the only unit that gets left is liter, right? So when we initially calculate the volume of distribution, it'll actually be in just liters because the mass should cancel out. Okay, so what I'm going to do is I'm going to take that 100 milligram dose that I gave, and then I'm going to divide it by the concentration in the plasma. And when I do that, I get an AVD of 40 liters. Now this is really important. What does this mean? Well, it should be pretty obvious what this means, right? What this means is that 100 at this concentration, right? At this concentration here, and at this dose, that's telling me that this dose has diffused out evenly throughout the entire 40 liters of water. And this is what we would anticipate, right? We would anticipate that if I injected 100 milligrams into 40 liters of water, that drug would diffuse out and the concentration would be more or less evenly diffused throughout that 40 liters, and I would expect a volume of distribution of 40 liters, right? I would expect 100 milligrams to be dissolved, evenly distributed throughout the 40 liters. And this forms the basis for understanding the volume of distribution, right? If you guys understand this, then it'll be easier to understand what is going on when volume of distribution values do not equal 40 liters, because most drugs will not have a volume of distribution value that equals 40 liters. Okay, I think I'm going to cut the video off here, and then we will pick up the more advanced or more nuanced understanding of volume distribution in a subsequent video. Hopefully you guys enjoyed this, and hopefully it's making sense up to this point. Take care, and we'll see you in the next video.